Sick. All right. Well, welcome everyone. This is sort of one of the first sessions on how the BLCMDs work. Feel free to, yeah, basically the entire point of today is a recap of the video that I did sort of 6 months to a year ago now on how motor control works in general, but with more of a focus on the brushless side, not the brushed stuff. But if you've got questions on the brush stuff, I can answer that too. Yeah, so I've got some slides here to go through that sort of recap the important bits, but really it's up to you guys on if you've got any questions on those. Who, out of just interest, I'm not going to judge you. Who's had a chance to rewatch that video like recently? Okay, just so I know. Cool, that's all right. Does anyone have any questions up front? Because I can almost guarantee that none of you understand. Have all of you watched that video at least once or attended the actual video? Okay, you're going to be like severely out of depth, just as a heads up. But I'll try to get you up to speed. Sure. Yeah. Yep. The reference frames for the current are quite, it can be quite tricky. We will be touching on that. Anything else?
Where is the project on
it's under Christos's account. Talk to him to sort that out. Yeah. Exactly. Yeah.
Yeah, adding extra coils. I don't quite understand.
Okay.
Does it mean the output power is amplified by 3 times? Yeah, 3 coils.
Well, both. Yeah. No, that's a fair question. Yep. We'll also go into that. Sick. All right.
Will, you might need to like repeat the
Okay,
questions.
sure. Yeah, so Alex was asking about what the effect of extra coils in the motors does. Like, does it amplify the power by the number of coils you add? And Matt was asking where the GitHub project is, and the answer to that is it's on.
Cool.
So talk to him about that. We will merge it all in together at some point. Cool. Yeah, like I said on the slides, there's zero chance you all understand it all because I barely understand everything I'm presenting. So yeah, here's a quick recap. So in a brushless motor, it's a bit different to like the traditional motor that you would have been taught in like year 11 physics or something. There's no commutators and there's no brushes, hence brushless. It's essentially just a wheel of magnets and a wheel of coils, and you use the magic of control to switch how the coils are on and off to make the magnets get attracted to the coils in a way that spins the motor. So a bit of a lingo, the rotor is the part of a motor that rotates, and the stator is the part of the motor that is stationary. That's the easy way to remember it. But on a brushless motor, the stator has the coils. On a brushed motor, the stator has the magnets. So the magnets in a brushed motor don't move. The magnets in a brushless motor do move. So that's something to keep in mind. You might get that confused, but it's always best just to think about how they move in terms of their name rather than what they're made of. So the question is, how do we control these coils in order to make it actually spin properly? Cool. So a bit of background on DC motor behavior. You'll remember this slide from the last presentation if you watched it. The main takeaway from this slide is the big one: V does not equal IR anymore. It's not because it's not a resistive load, and there are extra elements at play. So the large scale, like the very detailed model for a motor is V equals IR. So you've got the resistive, the coils will have some resistance, so you'll get some voltage drop across that resistance. There's also an inductive term. So because the coils are essentially an inductor, right, a coil of wire, you will have a inductance times the derivative of the current term for voltage. So LdIdt, right? And that, so if you do a sudden change in current through the coil, you will get a corresponding step in voltage. Is that right? Yes. But the main thing that's important for a motor, so that inductive term does have effects, but it's generally fairly small on the scales we're talking about. But the main thing that is interesting is this VEMF term there. So the V equals IR plus back, it's called the back EMF. and it's a function of omega, and it's essentially linear with omega. Omega being the speed, the angular velocity of the motor. So can be a little bit unintuitive, but for example, if your motor is stationary and you apply 10 volts across it, you'll get, and say your resistance was 1 ohm. If it's stationary, the moment you connect 10 volts across it, you will get you'll get 10 amps across the motor, right? Because that back EMF term is 0. But if your motor is moving very quickly, such that it's generating 10 volts of back EMF, when you apply that 10 volts across the motor, the current draw will be 0, because you're applying 10 volts to a 10 volt source essentially, and the total current flow is 0. Does that make sense? That might be a new way of thinking about things that you might not have heard. Cool. For now, yes. So the question was, can you treat all the phases as balanced? The short answer is yes. The long answer is it's a little bit complicated, only because you can do some trickery by assuming that the central node isn't at 0 volts. If you let the central node float, you can get more power. We'll get to that. Yeah, but for all intent, like for the actual like maths, it's always like, yeah, you can assume it's balanced. You won't really, you probably won't ever really analyze a 3-phase motor, like a brushless motor, in the same way you would like a 3-phase induction motor or something in 3073. It's usually a bit simpler than that, but we'll get to stuff like that. Anyone else got any queries about this stuff? Sick. All right. So onto what Alex was talking about. Lots of magnets, lots of coils. So as you saw before in this picture, that motor on the bottom there has, I don't know, like 30 magnets and 28 coils or something, and that diagram above has two magnet pairs and 6 coils. So you can have oodles of magnets and oodles of coils, but the fundamental unit is this first diagram here. So you have 1 magnet pair and 3 stator coils. You can then double the number of magnets, double the number of coils, and you can double, and then you can do it again, and you'll always get, like the magnets are always like pairs, and the coils are always triples, right? Because you've got the 3 phases. So if we just look at this, if we just look at this first one, so we've got the south pole of the magnet, which I will say is blue, and the north pole that is red. And in this picture right now, we've got a sort of north pole generated at the C node, and a south pole at the A node. Now what that's doing, right, is so we've got this red north pole here. So C is actually pushing the red side away, and A is pulling the red side towards it. And at the same time, C is pulling the blue side towards it, and A is pushing the blue side away from it. Now you'd probably be able to tell that that's going to be a weaker effect than what's going on the north side. But as you increase the number of magnets, that weakness gets less and less, right? Because the distance between all of these phases gets smaller and smaller and smaller. Kind of. Yeah. So the question was, does more poles mean you can control it smoother? The short answer is yes. So this gets into this concept of we sort of call them electrical revolutions and mechanical revolutions. So if you have a motor with, say, 7 magnet pole pairs on it, it will do 1 mechanical revolution. And within that mechanical revolution, there will be 7 electrical or magnetic cycles of the control. So because it's going north, south, north, south, north, south 7 times per revolution. And you can actually just picture that as literally a spinning. You can picture that as this simple model, right, with the single pair rotating just 7 times per revolution. It's exactly equivalent. So what's your question? Sort of, does it make it smoother? Yeah. So it does. There's this thing called torque ripple. which sort of it depends on a lot of things. I think it can sort of depend on how far away the magnets are from the coils, and by having them closer together, that sort of linearizes it a bit more, makes it less angularly dependent. Alex?
So like in the first diagram,
Correct. Yep. Yep. So Alex was just saying if the rotor was slightly more angled so that the blue side was right next to B and the red side was in between A and C, that would be the point of maximum torque. So as you rotate, you can imagine as red gets closer to A, that element of the torque becomes like very, very small. And so the only bit of the torque you'd have is what the C pulling on the blue side, for example. But yeah, we will get more into that in a minute. Yes. Yes. So the question was, is like an induction motor, is the frequency, sorry, does the angular velocity or angular frequency of the motor itself depend on the frequency you drive the motor at? The answer is yes. However, we are essentially implementing a variable speed drive. So they're sort of interlinked. So as if we want the motor to accelerate, we will apply a torque and it will increase the frequency of the sinusoids. But the thing is, we don't actually see any of that because of the Clark-Park transforms. It's all abstracted away. Yeah, so we'll come to that in a moment. But yeah, so you don't have to worry about all that. All you have to worry about is applying a torque, and the Clark-Park transforms take the angle and do the calculations for where in the sinusoid you are. To answer your question, Alex, about the increase in power with more coils, I think the short answer is no. Having more coils doesn't necessarily increase the power, because it sort of increases the resistance of the system. It does. So one thing that does something that gives you more torque is having the motor physically larger, increasing the diameter of the motor, because it literally is just force times distance, right? So the wider your motor is, you apply a small force at a distance close versus a small force at a distance far away, that will increase the amount of torque you're outputting. So that's why the pivot motors are like this big. Yeah.
I mean, outrunners have large.
Generally, yes. The question was, would outrunners have more torque? So outrunners being motors where the magnets are on the outside versus inrunners where they're on the inside. Yes, generally that's true. Yeah, yeah, it's a bit weird, isn't it? Yeah, yeah, they're the magnets. Yep. Sweet. Okay. So we sort of touched on this in a moment. Sorry, a minute ago. This idea of like the ideal torque. So if we sort of abstract away the motor in itself, and we just think about we've got this spinning object, the rotor, and its angle is this gray arrow, right? If we applied a magnetic field to that rotor, that was in this purple magnetic field direction, right? We would get a component of that magnetic, or maybe instead of saying magnetic field, we'll say magnetic force, right? So we apply a magnetic force to the rotor in this purple direction, and that force acts in this blue component and this yellow component. Now that blue component, because we're thinking of this spinning rotor, right? That blue component, all it's going to do is push the rotor to the radially, right? Whereas this yellow component is acting perpendicular and it's going to push the rotor around, right? So this blue component is essentially wasted, and the yellow component is what's applying torque to the rotor. Correct. Yep. So ideally, the blue component would be 0, and the yellow component would be as large as you want it to be, right? As large as your torque you want it to be. So and we'll get to this in a moment again, but the reason why field-oriented control is so powerful is that you get that freedom to arbitrarily set that purple vector exactly where you want it to be within the accuracy of your sensors and all of that. Something like 6-step commutation, where you've got just like, so one in the, I'll jump to the other slides. Being very Facebook. Look at, sorry. We look at this slide. So this slide, there are 3 Hall effect sensors in the motor, and the Hall effect sensors, all they're doing is detecting essentially what magnet is in front of it. Is it a north or a south, or like somewhere in between? And from that, you can tell to 1/6 of an electrical revolution, 1/6 of a magnetic revolution, where the rotor is. So that's pretty reasonable, right? Because you might have like 7 magnetic revolutions per mechanical revolution, but you're not going to be able to tell exactly where it is. So this purple vector, so our knowledge of the gray vector is going to be slightly wrong. It's going to be plus or minus 30 degrees, and we're not going to be able to apply a purple vector that is exactly tangent to that, because we just don't know. Make sense? Sick. All right. Now onto the fun bit, current frames. So this is probably the trickiest thing to grasp when you're still learning. But I wish I've lost one of the graphs. I'm back. I'll jump to the same slide in the other presentation. So what the hell? Okay, I'll just do it like this. So there are 3. So these are current frames. So we can put the rotor aside for a moment, and we're just thinking about the stator. However, the rotor does come into play in a moment. So if we just picture the motor is spinning at some certain RPM, we're going to need to apply a current into the 3 coils as it rotates to pull it around. And what that looks like is this first graph here. So we've got these 3 sinusoids, and that is representative of the currents through the 3 coils. So when the blue, if we just look at this blue line, it's positive here, which means that we're putting positive current through that coil. So it's going to attract, say, the south side of the magnet. And then when it goes negative, it's going to attract the north side of the magnet. Okay? And we've got these 3 coils. And we're sort of representing this on this phasor diagram next to it, with these blue, red, and green arrows, which are the three coils. But we can see if we add them all together, we get this cyan vector, which is just tracing out a circle as it rotates. Yeah. So is that understandable? Anyone like really not getting what I'm talking about at all? Yeah. Yeah. So yeah, that cyan vector is actually the total magnetic field generated by the coils, and so when you add up all the vectors, that's the total magnetic field direction. Now you sort of might get confused, because you're like, well, we've got all these magnets. How does the total magnetic field direction point when you've got like 7 magnetic revolutions per mechanical revolution? The answer is that you need to just step back and look at it from this point of view, and just accept that abstraction layer of jumping up to 7 revolutions per mechanical revolution. Sorry, Harrison, what were you going to say? So this is another thing that can get a bit confusing, right? You've got a coil, and you run a current through that coil, and then that generates a yeah, it generates a magnetic field in a direction perpendicular to the current. So throughout everything I say, I'm going to be using effectively interchangeably torque, magnetic field direction, and current, because they're all essentially the same. You could like sit down with a pen and paper and draw out how the magnetic field directions work, or you could just trust me that it does work. So
I think what helps positive time.
I love dumb questions. So they each get one phase, but together you have three phases. Yeah. Yeah. So I'll keep moving through the rest of these current frames, or not even technically current frames. They can be voltage frames as well. Um, so, but yeah, they are very much, and in fact, if you look at them, that all of them say V instead of I. But yeah, it does sort of. I think once you start playing with the motors and understanding what's going on, you might get a better understanding for why, how you can just make the assumption that they're all like you've got these three phases of coils and current and magnetic field, and it's all kind of the same thing.
Is the current always lagging the voltage?
Matt asks, is the current always lagging the voltage? I might take a rain check on that. I think the answer is no, but it depends on the speed of the motor because of the back EMF. So when the motor is purely resistive, then they're in phase. Actually, no. Sorry, no. It does lag, but again, you don't see it because you're always operating in DQ frames. It just it turns it into essentially a linear system, yeah, instead of a rotating one. Yeah. Okay. We'll get to DQ frames in a sec. So the next frame is this alpha beta frame. So you can see, and we don't actually use this, but it's an important intermediate step. You can see that on the left we've got the ABC frames, but that blue arrow is only tracing out a two-dimensional circle, right? It's not traced. It doesn't have 3 degrees of freedom. It's only got 2 degrees of freedom. So what we do is we reduce that to essentially just an XY value, so alpha and beta. Unfortunately, this image isn't a GIF. I couldn't find where this came from to get it, but these diagrams are all really good. But you can picture that as this blue line as the cyan line rotates, like it does in this picture, the alpha and beta components will increase and decrease, and you'll get two sinusoids that are a sine and a cosine out of phase. Right? That cool? Okay. Now for the last one. Now this is probably the most challenging one, but once you understand it, it's really, really cool. This is the direct quadrature frame. So this is a rotating reference frame, and it rotates with the rotor. So you essentially take the you take the angle that the rotor is at, and you take the alpha and beta components, and you do what's called a Clark-Park transform to it. It might be an inverse Clark-Park, I can't remember. And that is essentially just a bunch of trig. It's just sines and cosines in a matrix, and that rotates your that I'm not doing a very good job explaining this. Hang on. So instead of having this blue line that's the cyan line that's traced out in the circle, you end up with you see these D and Q axes that are rotating with the cyan line. You then split it up into these D and Q components, and they're functionally, like you can see in that graph, they're not changing, right? So if we think back to this diagram, right, we've got this rotor position, this gray vector, and we want to maximize the direction of the current or the torque perpendicular. Sorry, we want to maximize the force perpendicular to create the most torque. We want to minimize the force radially on the motor, on the rotor. So you can see how this becomes useful, right? Because we can use this direct and quadrature frame to understand the component of our current and our voltage that's in line with the rotor, in line, and the amount that's quadrature or perpendicular to the rotor. So if we wanted to control these parameters, we could say this red line, the quadrature part, let's change our voltage so that that increases, and then this blue part that's doing nothing, let's decrease that component so it's 0. Now I get the feeling that didn't quite hit the mark for everyone. Where are people stuck? Alex?
So arrow is affected that would be cleared by some whatever
Yep. 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 So Alex was just saying we sort of linking it back to the original ABC coil. So that might be a good thing to do. So if we start on the right hand side, to go from the direct quadrature frame to the alpha beta frame, we just need to do one of the inverse transforms. I'm not sure if it's a Clark or a Park, to do that. So we essentially take the rotor information. It's this inverted matrix. We multiply that our dq vector by that, and we get this alpha beta vector, which is just rotating in a stationary reference frame, and it's just going around with two components. And then you can take that again, that alpha beta, and multiply it by the other inverse transform. Let's say it's a Clark, I can't remember. And that gives you the actual currents going through each individual. And in exactly the same way. So the way that for some inside baseball, the way that the control loops work, which we'll get to in a minute, but I might as well explain it partly here, is we measure the current through two of the coils, and because they're all connected together, we can infer the current in the third coil. So we measure the current in all three coils. So that's in the ABC frame. We then do the transform to put it into the alpha beta frame. We then do the transform with the rotor position to put it in the direct quadrature frame. So we then know the current that's in line with the rotor and the current that's perpendicular to the rotor. The control loop then goes, okay, I want to maximize IQ and minimize ID, right? Minimize direct. And then goes, what voltages do I need to apply to do that? Do I need to increase VD or do I need to decrease VD? Do I need to increase VQ or decrease VQ? So the quadrature voltage or the direct voltage. And then it goes, okay, I'm gonna change the voltages to be this value in DQ frame. Now, what do I actually need to apply to the coils, right? What percentage duty cycle do I need to apply to the coils? So then it goes back. Then it says, okay, I've got these voltages. What's the alpha beta voltages? Do you transform? Okay, got those. Do it again to get your ABC, and then you can send that information to your power stage to actually control the PWM. Yep. So Matt just asked, are we using the encoder to determine the phase angles? We're using the encoder to determine the rotor angle. So yes, so if we were using these Hall effect sensors, then yes, we would. Correct. So the encoder is accurate to, I think it's like 4,000 different positions per revolution. Now keep in mind that that's 4,000 per mechanical revolution. So actually, I'm trying to remember. I think it might be, yeah, it's like 1,000. Say it's 1,000. So divide that by 7, you get like 200-ish. Like potential angles per electrical revolution. 7 is used for the drive motors. So 7 electrical revolutions per mechanical revolution. I can't remember off the top of my head. I think it might be 12 for the pivot motors, or it might be even 20.
What drives the?
What drives that decision? So it's sort of it's the spec sheet of the motor. So the motors will have, a listed top part, like top speed and torque and torque per torque per amp and speed per volt. And you pick what you want, and you'll end up with a motor of a certain number of magnets. That's just how it works. Yes, I believe so. Yes. Yeah.
What tells you
What your requirements? So Alex asks what tells you your top speed. That just comes down to what requirements. So when we were designing the pivots, we were like, we want it to be able to do a quarter revolution, like 180 degrees in a second. And this is the reduction of the gearbox. So that means the motor has to move at this RPM. And then using that, if you watch the other video, you'll remember that there's the torque constant and the velocity constants at KT and KV. So KV is RPM per volt. So we can figure out how many RPM we need, and then we know how much voltage we can give, about 30 volts. So that'll tell us what torque constant, what KV we want.
what is the gearbox?
Yeah, that's fair. So yeah, if the gearbox designers are like, well, how much do we want? Like, we're going to design around you guys. Well, you just got to sort it out between you. Someone's got to pick. Yeah. One thing to note is that KV and KT, so your torque constant and your velocity constant, are inversely proportional. So you sort of so if you have a motor that has within the same motor scale, right? So if you have a motor that they're both like, say, 900-watt motors, and one has a really high kV and one has a really low kV, then you can implicitly tell that the one with a high kV is going to have a very low KT, and the one with a low kV is going to have a higher KT. So you'll be able to get more torque. So you sort of get an inbuilt gearbox in the motors depending on their geometry. And so a motor with a high KT will be pancake. A motor with a low KT will be very skew. All right, cool. Any questions at home, by the way, on anything on Zoom or Ruby?
Oh, good. Wait, just to like summarize though, like the current frame stuff, we do all these transforms and stuff just to make the control loop of figuring out how we reduce the radial current component.
Exactly. So one thing that I haven't got in these slides, but I have got here is So if you tried to I wish this was an animated GIF, but if you tried to design a control loop that could control the alpha beta frames, right? So these are still sinusoids or sine and cosine, whatever. Control loops are good at controlling things that's very slowly, right? So if you had something like this, if you've got a motor that's moving at 600 RPM, right? That's 10 revolutions a second, and you've got 7 electrical cycles per revolution. That motor's moving 70 times, doing an electrical revolution 70 times a second. That means that you need to have a control loop that can track a perfect sinusoid moving at 70 hertz, which might be okay because 70 hertz isn't that fast. But if you move up to 6,000 RPM, it's a whole different kettle of fish. And tracking a sinusoid with a control loop is quite difficult. Tracking a smoothly varying thing like a DQ frame voltage or current is a lot easier. And makes it stable, right? If you had to do that for really quickly, you would just need really, really fast control loops, and it would get really nightmarish very quickly.
Awesome.
Yeah. It's not unstable. So Matt was asking, is there concern with the Clark-Park transform if you're putting garbage in, you get garbage out? Well, if you put garbage in, you will get garbage out. But if you have slight noise on your current readings, you will get just slight noise on your direct and quadrature readings. If you have a slight angle mismatch, that'll just create a slight angle mismatch in your clock in your current vector, right? Yes, it is. Sorry. So it's constant with application. It varies with angle of the rotor, right? So yeah, I'll just they depend on theta. So one, it's just a rotation. It literally is just a rotation matrix. So let's have a look at the Wikipedia page. So the Clark, here we go. The Clark transform, that's the one that converts from alpha ABC to alpha and beta. That is constant. That is just this matrix. That's it. The Park transform is a 2D rotation matrix. Now the thing that's a little bit maybe a bit unexpected. This is a three-dimensional matrix, and this is a three-dimensional matrix. They keep this. I don't know. Some of the derivations keep this like extra component for like pure maths reasons. Yeah, there's a zero vector, but it's just got no component in that direction. It's a bit weird. Anyway, this is just so that you don't have everything square matrices. I think so that the inverses play nicely. Maybe I don't know. Maths. I don't do it. Cool. All really good questions, by the way. This is great. Oh, that's the wrong slide. Cool. Oh, what the hell? How is that an animation? That's where it went. Okay. Whatever. Cool. So I kind of touched on this already. But so we use the DQ frame to convert from our coil currents into the DQ frame. We then do some control system stuff, get our DQ voltages, and convert those back into coil voltages. And this all depends on the rotor angle. Sweet. Go. No, that's okay. No. Current and magnetic field, yes. Voltage, no. Because of the back EMF. And we'll, yeah, so current and magnetic field, 100%. And I'll use those interchangeably. I'll probably only talk about current now. You can use current, torque, and magnetic field interchangeably because there is no direct component. So the force is perpendicular always, and therefore is only torque. And all of the current turns into magnetomotive force. Cool. And then this is also what I said. So we use the PI loops to control the QD voltages, and then that gets converted back. Oh, far out. Okay, here we go. Space vector PWM. This is probably the hardest thing conceptually, other than harder than the DQ frames. And I wish I had studied up on it a bit more for this, but we will see how we go. Essentially, if you think back to like a brushed motor controller with an H bridge, you can PWM one side, and that gives you some somewhere between 0 and 100% voltage on the motor, sorry, on the motor wires. So we can do the same thing, but now that we've got 3 wires, it's a little bit more complicated. Let's start with a simple example, which is sort of demonstrated in this middle hexagon here. So these are all the possible states that we can put the inverter in, right? So the inverter is 6 MOSFETs, and you can have, and they're in pairs, and in between them is connected to the motor wire. So for example, in this first one, we've got, I'm trying to remember which way the colors go. I think red means on. We've got the A coil connected to the positive voltage, and we've got the B and C coil connected to the negative voltage. So in our application, that would be A is connected to 30 volts and B and C are connected to ground. So what that means is that current flows into the A coil and out of the B and C coils. It splits between them evenly. And so you would get a strong magnetic field generated through the A coil and a weaker magnetic field generated through the B and C coil in the opposite direction. So that magnetic field would be half and it would point the opposite way. So the A might point inwards and the B and C might point outwards. And then that would create and then you add those magnetic fields together and you get that magenta vector we were talking about before. This guy, you get that? Does that make sense? That was a lot. Matt asks, are the coils connected in Y? It depends. Usually, yes. It doesn't matter. Yeah, because you can always do a transform between them. Although, yeah. So you could sort of split the. Yeah, it is weird. It doesn't matter, but I understand the confusion. Yeah. At least I don't think about this because I don't actually know how our motors are wired. You can always correct, yeah, and just pretend that it's doing that. Yeah. Yeah. There is a central node, but we don't have access to that. Sometimes you can, but we don't. Mm-hmm. Mm-hmm. Good thinking. No, they're wired in series, or maybe parallel. They're wired together, probably parallel. Yeah. Are connected together. Yes. So so all of the A wires are we'll say parallel. I'm pretty sure it's parallel. All of the A wires are connected together. So actually, we might be able to see. So see all these wires on the back of the motor here. That's them all connecting together. So you've got like this wire, this coil here is connected to this one, is connected to this one, is connected to this one, is connected to. And this exactly, and this is exactly why you can ignore the fact that there's 7 electrical cycles, except for when you're doing all the transforms, because that it is equivalent, right? Yeah. It's nearest one. Yeah, it's interacting with only the 3 nearest to it. Yeah. So yeah, so they're enamel wire, so they're covered with like nail polish almost. Yeah. But it is so if you start to smoke a motor, you'll smell a lovely smell. That's the enamel boiling off. And it's sort of an accelerated effect because you'll burn the enamel off, then they'll start to short together, the resistance drops, the heat increases, etc. Correct. Yeah. Harrison? Yeah. Yeah. They are all so they're all connected in the middle in a Y. So if you have a, I think there's a diagram on this slide. Yeah, so maybe that diagram is helpful where you've got the 3 coils and they're connected in the middle. Ignore this because that's a brushed motor, but you've got the 3 coils and they're connected in the middle. And so if you have, say you had this purple one at battery voltage and these 2 at ground, the current would flow into this one, reach the center point, and then split between the other 2. Yeah. Cool. Yeah. Cool. All right. So yeah, that was like step 1. So this is the So the inverter is there to connect each of the ABC wires to either high, like 30 volts, or to ground. Yeah. So this is what space vector PWM is. So I'm going to be describing something that is probably more like what sinusoidal PWM is, but then I will go to later, probably another week because we're running out of time, on what the difference is with space vector PWM, and it's what you were talking about, Matt, with the centered node floating. Yeah, go. Should we? Yeah. Correct. Yeah. So you can't, for example, turn both the C1s on because then you'll get a short between battery and ground. And you can't turn them both off because then you'll leave the C node floating. And well, as to why that's not allowed, good question. It's yeah, because you want to control it basically. Yes. Yeah. Intermediate. Yeah. So okay. So to go into exactly what Noah was saying, we've got these 8 states. You can see the 2 on the right are either the whole top row is on or the whole bottom row is on. Correct. So no current can flow in those situations, because they're all connected to the same voltage, right? And then so we went through the one example here. I'll do one more. So in V4 here, you've got positive connected to B and C and negative connected to A. So current will evenly split between B and C, reach the center point, and then flow out of A. And then you'll get a magnetic field pointing, say, inwards for B and C. That's a half strength, and a strong magnetic field pointing outwards for A. And that will pull the rotor in the same direction. Okay, so they're all the states. Now, the way the PWM works is instead of just PWMing on and off for one half bridge like you would in an 8 bridge, you PWM between adjacent nodes. So an adjacent node is are they called nodes? Poles. Let's go with pole or vectors. Let's just go with vectors. You PWM between adjacent vectors. So an adjacent vector is a vector where there's only one half bridge switched. So for example, between V1 and V2, all we've done is switch B. Between V1 and V3, we've had to switch both A and B to get that, right? Sort of, yeah, kind of like gray codes, but that's not important if you don't understand what that is. And then, yeah, so you can see if we switch from V1 to V7, we need to switch 2, but if we switch from V1 to V0, we can just toggle A, right? So the first thing is, say we want to generate a voltage, right? We're generating voltages here. That's what we're doing, and then the voltage will infer a current through the loop. But this is just at the voltage stage. Say we want to generate a voltage that is in line with V1, but at half strength. Can anyone tell me what we would do? Okay, so you can't be in 2 states at once, but good guess. Harrison, what did you say? You said switching between V1 and V4? Yeah. So that's close. So if we did V1 and V4, well, there's one problem. We have to switch 2 gates at once. So V2 and V6. No, because you need to switch 2. Oh. Okay, someone did say it though. The answer is you need to switch between V1 and the null vectors, either V7 or V0, right? So in our case, the adjacent one is switching between V1 and V0. So if we look at this diagram down here, it's all rotated, but we toggle between this green one, which can be V1 in our case, and this blue null dot, which is V0 in our case, and we switch between those at 50% duty cycle, and we get this red vector at half length. Cool. Now the other one is, say we want to generate a vector that is between V1 and V2. Same length, just between. Exactly. Yep. So you toggle between V1 and V2. So that's really straightforward. And then what if we want to do between V1? What if we want to do one that's halfway between V1 and V2, but at half the strength? Yeah, so it's not quite that complex, but you've mentioned all the right things. So we would spend 1/4 of our time in V1, 1/4 of our time in V2, and half of our time at the null. Yeah, so exactly. Oh, you might be right. Yeah, so so yeah, it's a good question. So, little secret for you. We don't have to write the code that does this. It's just a block that does it for us. So you don't have to worry too much. It just works, is the answer. But it's good to understand what's going on under the hood. But the important thing is that you well, yeah. So one thing I haven't really mentioned is that we're spending time in one and then time in the other. Now, the reason we're allowed to do that is because the current, because of the inductance of the coils, the current gets smoothed out, right? So the inductance resists the changing current. So we spend some time applying this voltage, some time applying this voltage, some time applying this voltage, but on average, the sort of voltage applied, if you think of it as only a resistor and not an inductor, is in the direction we want it to be. Capiche? Sick. About 5 minutes left. Oh, you gotta go. Okay, we might. Okay, we're gonna leave it there. Thank you for coming.